Let's talk about the MOS capacitor, which will lead us to an understanding of the MOSFET threshold voltage. The top plate of the MOS capacitor is the gate, formed from a polycrystalline silicon, or poly layer. It's heavily doped so it acts like a metal. Underneath the gate is a thin dielectric layer formed from silicon dioxide and insulator. Below that is the bulk of the semiconductor, in this case, a moderately doped p-type region. The connection to the backplate is made by a heavily doped p-type region. We see the P plus indicating heavy doping. The actual body contact or back contact would be made at the silicon to silicon dioxide interface where all the connections are actually made, but here we show it at the back. The doping of the semiconductor is moderate. Its minimum doping would be on the order of 10 to the 15th carriers per cubic centimeter, up to a maximum of about 10 to the 18th. The corresponding room temperature potential would be about 0.3 volts up to about 0.48 volts. As you apply a negative voltage on the gate with respect to the bulk, an electric field is formed which attracts holes to the surface where they accumulate. The capacitance of the structure is given by the change in the charge due to a change in the gate to bulk voltage. The structure forms effectively a parallel plate capacitor. The area of the capacitor is just the area of the gate, the width times the length, and the capacitance per unit area is Cox, which is the ratio of the permittivity of silicon dioxide to the oxide thickness. The permittivity of silicon dioxide is about 3.9 times the permittivity of free space, and the oxide thickness is in the range of 10 to 100 nanometers. As the voltage from the gate to the bulk is made more positive, holes are driven away from the silicon to silicon dioxide surface, forming a depletion layer, which is analogous to the depletion layer in a p-n junction. Here we're assuming that the doping underneath the gate is constant as a function of position, and that depletion extends from the surface at x equals 0 to a depletion layer depth of xd, which we're about to compute. The total charge of the region is given by minus Q times the concentration of acceptors in the bulk times the depletion layer depth. The area of that region allows us to compute the maximum electric field, which is just given by minus the charge over the permittivity of silicon. The total charge is Q times the doping times XD, and the permittivity of silicon is about 11.7 times the permittivity of free space. This forms a built-in potential, which we can find by finding the area of this triangle, which is 1/2 the base, which is XD, times the height, which was the maximum field, which we found from this equation. So if we plug that in, we get an equation for the surface potential as a function of depletion layer depth. If we solve that relationship for the depletion layer depth, we get an equation of the same form that we had in the for the width of the depletion region in a p-n junction. If we multiply it out, we find that the charge is proportional to the surface potential to the 1/2 power. If we take the derivative of the charge with respect to the surface potential, we get what's called the depletion layer capacitance. Since this is phi sub s to the 1/2, when we take the derivative, we get 1/2 of phi sub s to the minus 1/2 power times these constants, and we get this relationship for the depletion layer capacitance. So in the depletion condition, the capacitance seen from the gate to the bulk is given by the series combination of the fixed oxide capacitance and the depletion layer capacitance, which depends on the applied voltage. This formula gives the result and shows that as we come from accumulation, where the capacitance per unit area is Cox, it drops according to this formula as we include depletion effects. Now notice that the surface potential can be computed using a voltage divider expression between the fixed oxide capacitance and the voltage-dependent depletion layer capacitance. Now, so far we've only considered the effect of depletion of the holes. But if there's a source of electrons available, then a second mechanism competes with depletion as we increase the gate voltage. As we increase the gate voltage, the electrons are attracted to the surface to form a so-called inversion layer. The surface electron concentration is controlled exponentially by the surface potential. And as the surface potential approaches 2 phi f, where phi f is this built-in potential, the inversion mechanism tends to dominate over the depletion mechanism. And as the surface potential approaches 2 phi f, the exponential increase in the electron concentration dominates over the depletion mechanism. And further increases in the surface potential predominantly increase the electron concentration, and the depletion layer depth no longer increases. So let's summarize the MOS capacitor. For negative voltage on the gate, holes are accumulated to the surface, and the capacitance from gate to bulk is just given by the oxide capacitance. As the gate voltage is increased, we begin to drive holes away from the surface, and the surface becomes depleted. Because of the increase in the depletion layer depth with the increased gate to bulk voltage, the capacitance is nonlinear. If there were no inversion layer formed, then the capacitance would just continue to decrease. However, assuming there are electrons available, for a sufficiently large gate to bulk voltage, we pass the so-called threshold voltage at which the surface potential is 2 phi f. For further increases in the gate voltage, the capacitance is dominated by the addition of electrons in the surface inversion layer, and the depletion capacitance becomes less important. The net capacitance returns to Cox W times L. Now let's talk about what happens if we add a heavily doped N-type source region that can supply electrons to the inversion layer. If the bulk and the source are at the same potential, then the equations are unchanged and the behavior is similar to what we discussed previously. However, if the bulk terminal provides reverse bias, then the equations for the surface potential have to be modified in the following way. We take the surface potential in all the equations and replace them by psi minus the source to bulk voltage. That shifts the threshold according to this formula, but everything else stays essentially the same as before. Previously, we had the gate and body terminals, and we added a source terminal. To complete the structure of the so-called N-channel MOSFET, we'll add a second heavily doped N-type region with a P-type substrate to form the NMOS transistor. You can also have a PMOS transistor where all the N's and P's are swapped. To build that structure, we start by diffusing an N-type well into the P-type substrate. Then the source is a heavily doped P-type region, the drain is a heavily doped P-type region, and the bulk is a heavily doped N-type region that makes contact to the N well. The form of the equations for the threshold voltage for NMOS and PMOS devices is the same, but some signs change. Also, there are sign changes depending on whether the gate is made of N-type or P-type poly. The threshold voltage is defined as the value of the gate to source voltage for which the surface potential is at the onset of strong inversion. Now, a negative charge at the silicon-silicon dioxide interface induces a positive shift in the threshold voltage. The threshold voltage is made up of a number of terms involving the differences in the materials properties of the gate and the semiconductor, and a number of charges that exist underneath the gate. For example, the polysilicon to bulk work function difference depends on whether the gate is heavily doped P-type poly or N-type poly, and the signs here are chosen to indicate which choice they are. And the built-in potential associated with the gate is either plus or minus half the silicon band gap. Now, depending on whether the substrate doping is N-type or P-type, corresponding to PMOS or NMOS FETs, we get a positive or negative sign on one factor of phi f, where phi f is given by our usual formula. The depletion charge can be positive or negative, again depending on whether it's N-type or P-type. We take the results of the depletion layer analysis that we did previously, including the effect of the source to bulk reverse bias. Now, we can group a lot of the constants into a parameter gamma, which is given by this formula. Now, most of the rest of the charges in the structure are usually negative, and therefore, according to these signs, produce positive shifts in the threshold voltage. For example, the charge on so-called surface states are brought out separately in this analysis. They change their state depending on the surface potential, and so that adds to the effective capacitance of the structure. And the charge in the surface states can vary randomly with a variety of time constants contributing to flicker noise. There are a number of other possible sources of charge, such as interface charges and mobile charges due to contamination. Usually these are not present. But one final thing is that you can intentionally do a so-called threshold adjust implantation, usually of boron atoms that are implanted close to the surface where they become negatively ionized. Because we have good control over the dose of implanted material, we can raise the threshold voltage to a carefully controlled amount.